This video is on conservation of energy. I'm Mrs. Estock. Let's get started. Conservation of energy means that no energy can be created or destroyed. Energy just keeps getting recycled and changing forms. This means that the same energy that was present the moment the universe began is still the same energy that is present today, including us. That's why Neil deGrasse Tyson famously says, "We are made of star stuff." Our bodies, our energy, is the same energy from exploding stars billions of years ago. We are just a recycled form of that energy. So we know that energy comes in many forms, and we know that we can transform that energy to different forms by doing work. When energy changes forms, it may shift from one type to another, but the total amount of energy remains the same. So the energy never disappears, it simply changes from one form to another. Now, keep in mind, there are really no types of energy. This is just humanity's way of describing what we see, our observations. So all the different types of energy really just boil down to energy. They're all measured in the same units, and they're all energy. We know there are ways to store and transfer energy, though. We can store energy in the form of potential, kinetic, thermal, sound, chemical, or light energy, and we can transfer that energy by doing work through temperature differences, through heating, or even radiation through electromagnetic waves. But no matter the form of energy storage or the way the energy is transferred, the total energy must always be conserved. So within a system, the total energy initial should equal the total energy final. This is the law of conservation of energy. Conservation of energy tells us that the total energy of a system remains constant if only conservative forces do work on that system. And by conservative forces, we're talking about the force of gravity and also spring forces. If only these types of forces do work on a system, then the total energy of that system remains the same. However, the total energy of a system will change if any non-conservative force does work on that system. Non-conservative forces include the force of friction, applied force, normal force, and tension force. If any of these forces do work on a system, then the total energy of that system will change. However, that does not mean that that energy appears out of nowhere or disappears from the universe. It just means it's been transferred to another system. Let's say friction does work on a system. It takes some of the energy of that system and removes it. And maybe that energy goes into the environment, dissipates as heat or sound energy. It doesn't mean the energy disappears, though. It just means that it's been transferred to another system. In class, when we look at the idea of conservation of energy, we're going to first look at mechanical systems. An ideal mechanical system is a system where the sum of the kinetic and potential energies, also known as the total mechanical energy, stays constant. So this is a system where energy is conserved, where the total mechanical energy, or TME, stays the same. It could be that the energy shifts from kinetic to potential or potential to kinetic, But when you add together the kinetic and potential energy at any given point in the motion of this object, the total energy or total mechanical energy should remain at the same value. Below I have an example of a roller coaster. It's about to get back up to the top, and we'll see that when it starts at the top of the roller coaster, it's all potential energy. And as that roller coaster moves through its motion, if it loses height, the potential energy transforms into kinetic energy. And if it gains height back, let's say over this next hill, some of that kinetic energy shifts into potential energy. But at any point during its motion, if you watch the total mechanical energy bar, or that green bar in the energy bar chart, you see that the total mechanical energy stays the same. In other words, the sum of the kinetic and potential energies at any given point remains constant. This is an example of an ideal mechanical system. There are systems that are non-ideal mechanical systems. This means as the mechanical energy changes or decreases, there's a corresponding increase in other energies, such as internal energy. Take a basketball that is dropped from some height and bounces. So this is a slow motion capture image of that basketball bouncing. And you can see that if it starts maybe from the left-hand side of the image and moves rightward, with each next bounce, the height of that bounce is getting less and less. So that means that the total energy is not staying constant in terms of the total mechanical energy. So in other words, if you were to add together the kinetic plus potential energy of those two different height bounces, it would not be the same. Well, where did that energy go? If you've ever watched a slow motion video of a basketball bouncing, when it hits the ground, that basketball squishes and deforms a little bit. When that happens, some of that energy changes into internal energy. The smushing or deformation of the ball increases the heat of it, and it turns into internal energy. So that's where the Q on this equation comes from. So in this situation, we have to consider not just the total mechanical energy, the kinetic and potential, but also the internal energy of the system to account for where that total energy goes to. So a situation like this we call a non-ideal mechanical system. But keep in mind, with either type of system, the total energy is always conserved, because energy, like matter, cannot be created nor destroyed. For example, let's say that we push a chair across the floor and it comes to rest. Let's think about the total energy in this system. To begin with, when we push the chair, we're applying a force to the chair, adding energy to the system, and we transfer energy stored in our bodies in chemical form to the chair. The chair stored that energy as kinetic energy due to its motion. So now the chair possesses that energy, and we can see it in the form of kinetic energy because it's moving. What happens next? Well, as the chair slides, it still has some kinetic energy because it's still moving, but we know that chair is going to slow down and eventually come to a stop. Where does that kinetic energy go? Well, because friction is doing work on the chair, some of that kinetic energy gets dissipated because of that non-conservative force doing work on the system. This dissipated energy is stored as thermal energy in the ground. So the ground gets a little warmer, the temperature increases because of that friction force. Eventually, the energy is stored entirely as thermal energy as the chair eventually comes to a stop. So eventually all of that energy gets dissipated to the environment and is stored as thermal energy in the ground. If I were to chart out what we just discussed, this example of the chair, showing maybe we start out by giving 4 units of energy. Maybe you can think of it as 4 joules of energy to the chair. So our bodies start with 4 units of energy, and we transform that energy from our bodies into the kinetic energy of the chair. So notice the total here is still 4. We began with 4 units of energy. We still in total have 4 units of energy. So in each transformation, we're looking to see how that energy total stays at 4 or stays the same. As the chair slides across the ground, some of that energy turns into thermal energy. And maybe some turns into sound energy because we can hear the scraping of that chair across the ground. But notice our total is still 4. So even though that energy gets dissipated to the environment, 4 units of energy are lost to the environment. So every amount of energy that we put into the system can be accounted for what is dissipated to the environment, or in other words, lost from the system. Now that we have a conceptual understanding of what conservation of energy means, we're going to put it into an equation form. So we know that the total energy has to stay the same. The total initial energy must equal the total final energy. Well, we have to account for all the different types of energy. We know that energy can shift from kinetic to potential. So if we talk in terms of the total mechanical energy, we know the sum of the initial kinetic and the initial potential energies must equal their sum final. If needed, we can also break each one of these terms down into its own individual equation. Kinetic energy, remember, is 1/2 mv squared, and potential energy is equal to mgh. So if we had to, we could substitute in these equations for kinetic and potential energies, keeping in mind that all energy is measured in joules, mass in kilograms, velocity or speed in meters per second. G is 9.81 meters per second squared, and our height would be measured in meters. Let's first practice writing our equations before solving. A woman stands at the top of a 20-meter tall building and throws a ball upward at 15 meters per second. Suppose we had to solve for the maximum height the ball reaches. If we're assuming that the potential energy at ground level is our 0 point, we're starting with the equation total energy initial equals total energy final, where the total is the sum of the kinetic and potential energies. We know that at its final point, the potential energy will be equal to 0. No, that's incorrect. There we go. Sorry about that. Something got shifted here, because when I said it, it did not make sense. So we know the kinetic final energy will be 0. The reason for this, just to clarify, the final point is when the ball is at its peak, right? So when this object reaches its peak, its velocity will be 0. And for that reason, we can say that the kinetic energy final will be 0. Sorry about that. And now we can break that equation down into its more detailed parts, where kinetic energy is 1/2 mv squared and potential energy is mgh. And if we were able to plug all of our values into this equation, we could solve for that final height. In other words, how high up it travels depends on the initial kinetic energy it was given and also the initial potential energy it had from starting 20 meters above the ground. We're not actually going to solve for h here, but this is how you would set up the problem. Let's say we had to solve for the velocity of the ball when it hits the ground. We're going to start with the same idea, kinetic initial plus potential initial is equal to kinetic final plus potential final. All right, this one I think doesn't need any changing. This makes sense. So when the ball hits the ground, the final potential energy will be 0 because when it's on the ground, it no longer has any height. So if we were solving for how fast the ball is going when it hits the ground, we could use our conservation of energy equation to solve for VF. Also, keep in mind here that kinetic energy is a scalar, so the direction of our velocity is not going to be accounted for in our solution. So when it hits the ground, we know that the final velocity will be pointing downward, but that's not going to appear in your solution for VF here. So if you were to be asked for the direction of that velocity final right before it hits the ground, that would be something that you'd have to add on at the end, that it's downward, or if vector-wise you're making up positive, then your downward pointing vector would be negative. All right. Now that we've practiced setting up some of these equations, let's try solving one of the problems. A 2-kilogram ball is dropped from rest off a 50-meter high cliff. First, I've drawn the motion diagram for this problem so that I can get a clear picture in my head of what's going on. The ball is dropped from rest. It starts 50 meters off the ground and falls that 50 meters to the ground and accelerates while doing so. Again, let's assume that we're going to set potential energy to 0 at the bottom or at the ground. And now we're going to solve for the kinetic energy of this ball at 25 meters above the ground. So 25 meters would be the halfway point in its fall, when it still has some potential energy because it's not at ground yet. And now it's moving, so it has kinetic energy as well. So beginning with our potential energy, kinetic energy, conservation of energy equation, we know the total mechanical energy initial is equal to the total mechanical energy final. We're solving for the final potential energy. And because this ball is dropped from rest, we know it starts with no kinetic energy or no motion energy. So we're going to set KE initial to 0. Next, let's break down our potential energies into the equation mgh for both initial and final. And from here, we can plug in our values and solve for kinetic energy. The initial potential energy is equal to 2 kilograms times 9.81 meters per second squared for G. And our initial height is 50 meters off the ground. We're solving for our final kinetic energy. And our final potential energy at 25 meters would be equal to its weight multiplied by 25 meters. This simplifies to 980 joules is equal to kinetic energy final plus 490 joules. Subtract 490 from both sides, and you get 490 joules. So that solution should make some sense here because it's half potential energy and half kinetic energy of its total energy at that halfway point in its fall, because 25 meters is the halfway point of the total height, 50 meters. How fast is it going at 25 meters? What is its velocity at that point? Well, now that we have the kinetic energy at 25 meters, we can use Ke equals 1/2 mv squared to solve for its velocity at that point. The kinetic energy is 490 joules, what we just solved for. That'll be equal to 1/2 of its mass, 2 kilograms, times v squared. The 1/2 and the 2 kind of cancel, but the units make it so that v squared is equal to 490 meters squared per second squared, so that when you take the square root of both sides, you're left with a speed of 22 meters per second, or a velocity with direction of 22 meters per second down. And notice here again, since kinetic energy is a scalar, you're not going to get that negative sign at the end of your solution. So adding on that the direction is downward is something that you just have to think about and add on at the end, if you're being asked for the direction. Okay, last but not least, the work energy theorem. So to connect the idea of work to the idea of conservation of energy, the work energy theorem tells us that the work done on an object is equal to the change in total energy of that object. So this is the last part of that work equation that we talked about a little bit before, where by doing work, yes, you apply a force over a certain displacement, but the result of doing that work is a change in the total energy of the system. Because work is a way of transferring energy into or out of a system. So however much the energy of that system changes, that's going to be equal to the amount of work done. One last practice problem to wrap up this video lecture. A 0.2 kilogram toy car starts from rest and is pushed on the ground for 4 meters until it reaches a speed of 3 meters per second. Find the total change in energy. Well, the energy of the toy car changes because work is done on it. That applied force of pushing the car, some distance of 4 meters, changes its speed from 0 to 3 meters per second. So the work being done changes the total kinetic energy of the toy car. It doesn't change the potential energy though, because it remains on the ground the entire time, so its height doesn't change. So that means the work being done, or the total change in energy, is responsible for changing the kinetic energy of the car. Also, we know the toy car starts from rest, so the initial kinetic energy is 0. So really, the change in energy is equal to the final kinetic energy of the toy car. In other words, if it started with 0 joules of kinetic energy, however much kinetic energy it ends with must be equal to the change in energy of the system. I can solve for that final kinetic energy by plugging in my values. 1/2 of 0.2 kilograms times 3 meters per second squared gives me a final kinetic energy of 0.9 joules. And because work is equal to the total change in energy, the work being done must be equal to that final kinetic energy, which is the same value, 0.9 joules. And if I know the work being done, I can calculate the amount of force exerted on the car, or that applied force that caused the car to change its total energy by doing work. So energy was transferred by that applied force, making the final answer here for the amount of force exerted 0.225 newtons.